Asking for the differential amplifier specified in problem 9.2, let vG2 is equal to 0, vG1 is equal to VID. Find the range of VID needed to steer the bias current from one side of the pair to the other. At each end of this range, give the value of the voltage at the common source terminal and the drain voltages. Okay, so here they are saying that steer the bias current from one side of the pair to the other. So it means what we have to do is we have to turn off one and turn on one, and then turn off this one and turn on the other one. So we have to do two steps like that. So we have to first, if we turn this one off, then all the current flowing through this one should be going through this, and we have to calculate all the values right here. So here they are asking us to find out the input differential voltage. Input differential voltage is nothing but the VGS1. If I look at the Q1, that is the first one. So for that one we can call this one as VGS1, that is VGS, that's gate source voltage 1 plus the VS. Okay, and do we have all the values available? VS is negative V threshold, that one we can find, but we don't have the VGS value available. But if you look at this, we have the Kp prime W over L, that is available, and we have the threshold voltage available. We also have the current available, so we can calculate this value by applying the current equation. Current equation is given by I is equal to half mu1 COX W over L, or instead of mu1 COX you can put Kp prime as well. Actually mu P COX, because this is a P Mosfet, you can see the arrow is pointing inward, so that's mu P COX. Instead of mu P COX we can put Kp prime as well. So this is going to be half Kp prime W over L times V over drive square. V over drive is nothing but VGS minus V threshold, so we can put that one right here because we are interested in finding the VGS. So instead of V over drive I put the VGS1 minus V threshold, that is VTP in this case because this is a P Mosfet. Okay, now let's go ahead and plug all the values. I current is 0.5, but before I plug in values it's better to rearrange this one and put it in terms of VGS because that's what we are interested in, and the input differential voltage is given by this. Okay, let's rearrange this equation. So this is going to be, if I rearrange this one, VGS1 minus VTP whole square, that is equivalent to 2i times length divided by Kp prime W. Okay, you can also put it like 2i over Kp prime W over L, that one also works. Okay, and this one is equivalent to VGS1 minus VTP, and to get rid of the square root we can square root both sides, so this one will go away. This is going to be square root of 2i over Kp prime W over L. Okay, so this is what we have, and then we are just interested in VGS1, so we can move the VTP to the other side as well. So this is going to be VGS1, that's equal to square root of 2i over Kp prime W over L, and that one plus VTP. Okay, this is the equation we have. And here we can do some adjustment to make it look a little bit better. What we can do is, like, if you look at there's an equation for the V over drive that is given by this. V over drive is equivalent to negative square root of I over Kn prime W over L. Okay, if I bring this pattern here, I can simplify this equation using VOV. This VOV right here. Okay, and if you compare this one and that, the only difference is we have a 2 multiplying here, So if I take the 2 outside of the square root and put this term alone, instead of that term I can substitute this VOV over there. So if you do that, then this is going to be VGS1 is equal to square root of 2 times square root of I divided by Kn prime W over L plus VTP. And instead of this one I substitute VOV, and that's going to be a negative VOV because this is positive. So instead, to make this one equal, this value is equal to negative VOV. So instead of this one we can put negative VOV. So this is going to be negative square root of 2 VOV plus VTP. Okay, that is equal to VGS1. And we are interested in input differential voltage, and that is given by VGS1 plus Vs. And instead of VGS1 we can substitute this one over there. So that equation becomes V input differential equal to VTP, this is VTP minus square root of 2 VOV, and there's a Vs also addition right here. If you look at this, here we have a plus Vs, and Vs is nothing but Vs is equal to negative VTP. Okay, so instead of Vs I can put a negative VTP right here, and from this one you can see VTP cancels. We will just end up with negative square root of 2 VOV. And this equation for input differential voltage you can always memorize, because if you see a circuit and if the one of the sides is off, you always end up having this equation. VID input differential voltage is always going to be negative square root of 2 VOV. Let's say if you have the current flow equal, like let's say here we have 0.5. Currently we assume we are taking this one to be off and all the current are flowing through this. But let's say you have equal current flowing through this. Let's say you have 0.25 going through this, 0.25 going through this. In that case the VID is going to be 0 because VG2 is 0, and if the current flow, then the gate voltage should be equal. So VG1 also 0, and VG1 is equal to VID, therefore VID also 0. Okay, you can use that. But let's say you have different current flow. The current case we are looking at is one of them is off. But let's say you have current flow, but the current is not equal, but you have a current flow. In that case you had to use another equation that is given by, okay, let me write that one as well. That is given by VID is equal to 2ID1 over I minus 1 VOV. So this is the equation you will use if you have a different current flows, like there's a current flow but different values. So these are the different situations. If it's equal, that's going to be 0. If it's different, you use this. If one of them is cut off, then this is the one you end up deriving. VID is equal to negative square root of 2 VOV. Okay, and each side is going to be positive and negative, because when I take one side, like let's say if I'm getting negative value here, then in the opposite side the VOV is going to be a positive, like the sign is going to change. One is positive side, one is negative side. So that one also you have to be mindful of. Okay, that's the only difference. So currently we end up deriving VID to be negative square root of 2 VOV. Now let's go ahead and try to plug all the values, and also VOV is equal to, VOV is given by, first we can take the positive value of it, that is if you assume this one as positive, then VOV is going to be positive I over Kn prime W over L. So if I take this one positive, when I do this for the other side I have to take the VOV negative. That's the only difference, and this is KB prime. Okay, so let's substitute that one over here. So this is going to be negative square root of 2. Instead of VOV I substitute this one, and that's the, okay, that is going to be square root of 2, square root of I over KB prime W over L. Okay, and we can bring this square root of 2 inside as well and write it as 2. That way it will be easier. Okay, let me 1 second. Yeah, instead of putting the square root of 2 outside, I can also put it inside. So this is going to be negative square root of 2 and all these values, and negative 2, and the I value is known because we are assuming one of the side is cut off, so this current must be flowing through this, so the current flow through this should be 0.5 milliampere. So the value for the I right here is 0.5 milli, and the Kp prime W over L is provided in the question, that is 4 milliampere per voltage square. So I put the 4 milli right here. So 4 milli cancels each other. 2 times 0.5, that's 1 divided by 4, that is 0.25. If you square root 0.25, that's equal to 0.5, and since we have a negative sign here, that is negative 0.5, and that's the VID voltage in this side. If we assume one of these regions, this Q2 is cut off and Q1 is on. Now what we are going to do is we are going to do the opposite. We are going to assume Q1 is cut off and Q2 is on. So we are going to end up having exact same equation, that is the one we derived, that is VID. Okay, hold on, my pen is not writing. Let me double check why. Maybe I create a new page. Okay, now it's working. Okay, so the equation we derived is VID is equal to negative square root of 2 V over V, and if we go to the other side of this Mosfet, the only difference is now the V over V is going to be negative value. Before we had it to be positive, and now we are going to have it to be negative. So this is going to be negative square root of I divided by Kp prime W over L. Okay, plug in all the values like the one we did before. Instead of writing the square root outside, we can also write the 2 inside of this equation. And also, since we have negative cancels and become positive, so this is going to be just positive value, and this is going to be 2I divided by Kp prime W over L. And then if we cut off this region, then all the current must be flowing through this. Then this 0.5 milli, 2 times 0.5 milli, and Kp prime W over L is nothing but, that is given in the question, that is 4 milliampere. So 4 milli in the denominator, milli cancels, 1 over 4, that is 0.25, and if square root that one, that is 0.5 voltage. So the range of the input differential voltage is going to be negative 0.5 to positive 0.5. Okay, so that's the range. Now the next thing is we have to find out all the voltages. One of the thing we can find is Vs. Vs is nothing but negative V threshold, in this case VTP. That is provided in the question. VTP is already there, that's negative 0.8. Then this is going to be negative 0.8. That's going to give us positive 0.8 voltage for the Vs. And if you look at the drain current, drain voltage, that's VD1. VD1, here we can apply the KVL right here. VD1 should be equal to the voltage drop plus this voltage if you apply KVL. So let's write the equation for this. VD1 is equal to, the voltage drop is going to be resistor times the current according to Ohm's law. V is equal to I times R. So that is 0.5 milli times the resistance right there, that is 4 kilo ohm, 4K minus this voltage right here, that is 2.5. Okay. it's basically VD1 minus this should be equal to this, but you can rearrange and write it like this as well. And 0.5 millikilo cancels each other, and then 0.5 times 4, that is equal to 2, and 2 minus 2.5, that gives us negative 0.5 voltage. That's the VD1. And if you look at VD2, that's this one, and if we turn this one on and if we cut off this one, then there's no current flow, so there's no voltage drop right here. So it means VD2 is equal to 0 plus this. 0 plus negative 0.5, negative 2.5, that is just negative 2.5. So the VD2 is just negative 2.5 right there. And that is all required to find. I hope you guys found this video helpful. Thanks for watching. Don't forget to subscribe my channel. See you guys on my next video.